Welcome everyone. My name is Damir Rahimov. Please let me know if you have any questions. And yeah, I would also ask, can hear me properly? So let me share my screen and start. Okay, today we're going to continue our discussion on the correlation for deterministic signals. And I hope that we complete everything for this topic today. And next time we're going to start discussion about correlation for stochastic signals. And please let me know if you have any questions for video that I published the last week, because I didn't have tutorial and I uploaded video, recorded video Nextcloud. So, are there any questions regarding material that we recorded last time? So, as I remember, the question was we discussed, or I discussed the example where we have sequence of rectangular pulses. Had sequence of rectangular pulses, and then we had to calculate the correlation for this sequence. And the idea that we just can decompose it for two parts, for sequence of delta pulses and rectangular pulse, by calculating separately correlation function for each part, you can find what will be the resulting correlation function. You can also calculate correlation directly, just shifting this signal by different delays, and then trying to find what's the overlapping area. And also found the energy spectral density by calculating Fourier transform of correlation function. And finally, and that's it. Then it was another question. We had the sequence of rectangular pulses, and we had to find also correlation function. But it was similar to previous task. So, but today we're going to actually continue discuss all these questions. And are there any questions or comments? Don't see any so far, so I think we can start discussing next task. So, and we start with task number 3.3, which is the following: that you have delta pulse, and our goal is to find autocorrelation function and energy spectral density for delta pulse. And we try to analyze how can we calculate it. Yeah, and I would like to remind that we start 5 minutes before 9, so please come earlier next time. Okay, so we have delta pulse, and just remind you how it looks like. Oh, centered at origin, and it has magnitude equals to 1. It means that amplitude for delta pulse equals to infinity, but area under the function equals to 1. See that it's our signal x of t, function of time. And we need to find the correlation function and spectral density, energy spectral density. And we actually have two ways how we can find it. I show both options, how we can calculate correlation function. And first option, you just calculate correlation function via spectrum of delta pulse. For first step that we do, we calculate spectrum, go from time domain to calculate Fourier transform. We show how function x of f will look. X of f. And you remember that if you have delta pulse, Fourier transform of delta pulse will be constant. Amplitude or this value equals to 1, or it equals to magnitude of original delta pulse. Now we are in frequency domain. Next, we can actually find energy spectral density, because you remember that if you know spectrum of your signal, by calculating absolute value squared of your spectrum, you can find energy spectral density. And for this example, it's very simple, because if you have just line with line that goes amplitude 1, correct to say amplitude 1, but okay, this line that goes through the point 1. Then if you calculate square value of it, it will be the same line. It will be just line that goes through the point 1. All the same line. But I say that this plot corresponds to energy spectral density. It's not spectrum, it's energy spectral density. It's xx of f, which we find as absolute value of x of f. Yeah, maybe down a little. Oh, it will. And now, you remember that if you have energy spectral density, you can find autocorrelation function by calculating inverse Fourier transform. And for such function, it's very calculate for, because if you have just a line, after inverse transform, you get delta pulse. Then now I can show how correlation function get delta pulse, centered at origin, and it has same magnitude equals to 1. But now we say that it's our correlation function, autocorrelation function. Ixx of tau. And you see that if you take delta pulse and calculate autocorrelation function, get another delta pulse. And if you have original amplitude equals to 1, magnitude equals to 1, then for autocorrelation function, magnitude will also be equal. But if you have different magnitudes, then you have to calculate square of it. Okay, it was first option how we find autocorrelation for delta pulse. Another option can find autocorrelation function by using approximation of delta pulse. You can approximate delta pulse by rectangular pulse. So let's say this is our approximation, and this rectangular pulse, we assume that it has very small duration, delta t, and we try to make it as small as possible. And as far as we're talking about approximation of delta pulse, if, I mean, you remember that for delta pulse, area under the function equals to 1. It means that if you multiply amplitude by duration, you must get result equals to 1. And taking this into account, we say that actually amplitude will be equal to 1 over delta t. And then if you take 1 over delta t times delta t, it will be equal to 1. So when we 1 over delta t equals to 1. This is our approximation of delta pulse. So next step, yeah, what else I need to do? Also, I say that area delta pulse must be equal to 1. And now what actually I'm going to do, I'm going to calculate what's the energy of this approximated delta pulse. Because for next step, when we calculate autocorrelation for delay equals to 0, calculate energy. 1 over delta t times delta t. to 1 over delta t. And this is amplitude of autocorrelation function for tau equals to 0. I show this autocorrelation function below. But of course, you remember that if you have a rectangular pulse, autocorrelation function will be a triangular function, triangular pulse. Autocorrelation of my approximate pulse, function of delay. For tau equals to 0, I just use energy that I have calculated before. I see that for tau equals to 0, amplitude of autocorrelation function equals to 1 over delta t. And this triangle goes from minus delta t to delta t. Function goes from minus delta t. And now, question: what's the magnitude? Because let's say we have this is our autocorrelation function, and if we put delta t equal going to 0, say that delta t is very small and it's going to 0, then this triangular pulse will become very narrow and more narrow. And at some point, we actually say that, oh, okay, it's so small so that we can say that it's just delta pulse. But at the same time, keep in mind that if we increase delta t, 1 over delta t will start to increase, start to grow up, but the width of this triangle will be. And the next question, but okay, at some point when we achieve very small delta t, what will be the magnitude of this resulting delta pulse? These such parameters. Huh? And about it. So we have to understand what the magnitude of this delta of the correlation function. And I mean, again, definition for magnitude is area under the curve. And we have function here. We just need to calculate what's the area under this function. And it's triangular function, and we know how to find area of triangular. The magnitude, in this case. Again, in general, it's integral from minus infinity of our. In general, I write as delta pulse, but in our case, it's delta pulse in delay domain. Yeah? Not original delta pulse, it's different delta pulse that corresponds to autocorrelation function. Then we have to calculate this integral from minus delta t to delta t, our energy, or not energy, but I would say this approximation for delta autocorrelation function for delta pulse. We have triangular function, and so how we calculate area is just 1 over 2 8 times v. 8 equals to 1 over delta t times 2 times delta t. This is the width of our triangle. As a result, you see that resulting magnitude equals to 1. So it approximates quite well our. No, it's not. We don't say anything about that. It's approximates, but in general, we have magnitude equals to 1. And next step, we just do the following. Actually, I already mentioned it. We just say that we put delta t going to 0. Now, and then delta t going to 0. And in this case, our triangular becomes delta pulse. Becomes delta pulse is magnitude equals to 1, because magnitude doesn't depend on delta t. See that they cancel each other. And it just equals to 1. And this is the proof that you have for delta pulse, autocorrelation is another delta pulse with squared magnitude. So, and last step, we just say that, okay, if you take this autocorrelation function, then you find our spectral density, energy spectral density. You can find energy spectral density of our delta pulse is a constant. Amplitude equals to 1. And it goes from minus infinity to infinity. So that's it. And this is second way how we can show that autocorrelation function of delta pulse, the delta pulse. Okay, are there any questions? Because we distinguish these two notions, because for this signal that we consider right now, we have finite energy. Energy is finite. And if you calculate power, power will be 0. Because you have infinite duration of your observation, and you have finite energy. Finite divided by something infinite, it will be 0. But if when later we come to discussion about periodic signals, in periodic signals or stochastic signals, you always keep receiving or transmitting energy. Energy is infinite, and if you try to describe anything in terms of energy, you will have infinite quantity. And then we say that, oh, okay, but if we look to power, it's infinite energy divided by infinite observation time. But in case of periodic signals, we just analyze one period. It will be finite power. It will be constant. Okay, not necessarily constant, but it will be finite power. And then we can just easily describe our processes this finite power. And so for this reason, for finite signals or so-called energy signals, we use energy spectral density or energy correlation function, and for periodic signals or stochastic signals, power spectral density, and I don't remember if we any letter for energy. Okay, it was a question, yes. Okay, other questions? Okay, if not, then we go to next task. And actually, task number 3.4 that we're going to discuss now is very similar to what you could see recorded tutorial for last week. Because we have for task number 3.4, consider the following problem. We have signal u of t presented as u times sum of weighted delta pulses. So we have sum goes from 0, we have an times delta pulse t and capital T, and then convolution of t. And it's very similar to what actually we did for, I think it was task 0.2. I don't have a complete set of tasks now, but anyway, it was in tutorial last week. Okay, and we say that this sequence of symbols an have element plus 2, minus 2, and plus 2. It's our alphabet. And we also say that g of pulse shape function equals 1 over 2 rectangular function, and then we have t minus capital T over 4 divided by capital T over 2. Okay. And first, for this task, you simply need to draw all these signals, components. So I didn't specify that this expression in parentheses we denote as u delta of t. So we have to plot u delta of t, g of t, and u of t. Okay, let's start with u delta of t. And for u delta of t, you see that it's just the sum of 4 delta pulses. Each delta pulse has its own position on time domain, on time axis. You can just put different values for small n, and then you get position for delta pulse. And you have position 0, t, 2t, up to 4t. And for each delta pulse, we have specific magnitude specified by AN. And it's 2, 2, 2, minus 2, and another 2. Now I just going to plot it, and then we go to the next part. We don't have 5. We have only 4. We have 4. But I can keep it. And okay, for Z, we have delta pulse magnitude 2. For T, we have another delta pulse with magnitude 2. For free T, we have magnitude minus 2. For T, again 2. For 5T, it goes to 0. What signal? This is our signal delta T. Then next signal, more specifically pulse shape function. Pulse shape function G of let's see, it's duration of this pulse shape function T over 2, and at the same time it's shifted by T over 4 to the right. Tango pulse. And what's the amplitude? Amplitude equals to 1 over 2. Goes from 0 over T. Tango. Else. And finally, we need to plot task. Finally, we need to plot signal U of T. Oh, U of T is convolution between our sequence of delta pulses and pulse shape. And you remember that if you calculate convolution with delta pulse, it's one of the most easiest, it's just easiest possible convolution, because what you do, you just take your function and replace it instead of each delta pulse. And just do this sequence of rectangular pulses. Rectangular pulse, yep. Second rectangular pulse, 1, and fourth rectangular pulse with amplitude, last one. Okay, now we should be very careful about amplitude, because we have so many parts there. We have magnitude of delta pulse, we have amplitude of rectangular pulse, and then we have also amplitude of U of T itself. Now we have to multiply all these quantities. So times 2 times 1/2 gives us, that's right, that resulting amplitude U minus U0, yeah, negative part. And that's it. Go to next question, question B. Okay, good. Go to part B. Part B, to determine the discrete time autocorrelation function, and it's important, this is discrete time. It's in discrete time you have indices rather than time, and for this reason result will be have slightly different form. So determine the discrete time autocorrelation function of the deterministic length-5 sequence is defined as the discrete time autocorrelation function of finite duration signal, function of index, can be written as summation of n times a n plus m. And we already did something similar, but here I repeat it. And actually, the whole task is kind of repetition, but we just do it by a slightly different way, but almost the same. I'm going to plot table of possible shifts, our sequence. So, and we have these possible delays in terms of indices. We have 0 delay, delay 1, 1 index, 2 indices, 3. And I think it's enough. Then we have our original sequence, 2 minus 2, 2. And what we need to calculate, this discrete time autocorrelation. Calculate this by a function of m energy. So, and when we have shift by 0, just the same sequence, I mean, we multiply these two sequences element-wise and calculate summation. Do this, we have 4 plus 4 plus 4 plus 4, 5 times, result will be equal to 20. Then when we shift by 1, we shift it to the left, because it's finite sequence. If we shift it and we have nothing, we just place 0 instead of element. Calculate this element-wise product and sum. Result will be 0 because we have 8 minus 8. 0. And I shift this sequence by another index. I get 2 minus 2, 2, 0, 0. Okay, and we have what we have? We have 4 minus 4 plus 4, right? 4. Again, minus 2, 2, 0, 0, 0. And it will be 0. Result will be 0. And the last shift will be 2 and have 4 zeros. And the result will be 4. And we don't calculate further shift because the result will always have any overlap. Question? Yeah, the question how we calculate it. Yeah, idea was the following, that this, on top of this table, you have original sequence. Our original sequence. And what we do, we calculate element-wise product between our original sequence and shifted copy. And the index on the left side specifies this shift by how many elements we shift our sequence. So, and then for first line, we have no shift because shift equals to 0 indices. For second line, you see that actually our original sequence shifted to the left by 1 index. And because, and the first element we just remove because it will overlap with nothing. Yeah? So we have just zeros outside our sequence. then we would have to write 2 also, yeah, for original sequence. But because they don't overlap, don't do it, we just don't take into account it. And I also place 0 on the right side because 0 comes, I mean, outside our sequence, we have everywhere we have zeros. And we just write that we have 0. Then I make another shift for third line by another shift by 1. See that we have only 3 elements from original sequence. And every time I do shift, I calculate then element-wise product between shifted copy and original sequence. Then I calculate sum of these resulting products, and I place this result right side. How I calculate. And yeah, as a result, you see that we have these values for autocorrelation, 20, 0, 4, 0, 4. Okay, let's try to plot this function. Right side. So again, this is discrete time correlation function. A as function of difference between indices, energy. And for 0, let's say this is our point that corresponds to 20, value 20. This is not delta pulse, it's just how to call it? It's just how does it called? Unit pulse. Yeah, it's kind of pulse, but with limited amplitude. Yeah, you don't have error. It doesn't go to infinity. It has, now we can say that it has amplitude. Amplitude equals to 20, and that's it. But it's not delta pulse. It's just this sample. Yeah, it's sample. It has no duration and has specific amplitude. So, and then it's for point equals to 0. Then instead of time, we have indices. We have index difference between index difference 1, difference 2, 3, 5, minus 1, minus 2, minus 3, minus 5, and minus infinity. This is discrete sequence. How we get these numbers on the right side? I mean, you just calculate 2 times 2. You calculate this element-wise product between 2 sequences. What you get? You get 4 plus 4 plus 4. If I'm not mistaken, it should be 4 times 5, yeah, and you'll be 20. For second row, you do what you do. 2 times 2, it will be 4. 2 times 2, it will be 4. Minus 2 times 2, it will be minus 4. Minus 2 times 2, minus 4. And for last product, it will be 0. You have 4 plus 4, it will be 8. Minus 4, it will be minus 8. 8 plus minus 8, it will be 0. And then you always use as a reference first row, and you just multiply element-wise with next. No, it's element-wise product and then summation. And this is discrete time correlation. This is what we try to find. Okay, and yeah, this left column specifies difference in indices. For 1, result will be equal to 0. between indices 1, it gives us autocorrelation 0. For 2, it gives us 4. This is another pulse, is magnitude 4, amplitude 4. Then for difference 3, again 0. And for difference 4, it gives us, then it gives 0. All of the remaining processes will give us 0. Not periodic, it's finite. Then we can also extend it for negative range. We have 0, then we have 4, the pulse with amplitude 4, 0, another pulse with amplitude 4, and we have zeros. Then all the remaining points, they will be equal. But we get our autocorrelation function. Discrete time autocorrelation. Was it question? It was question B. And now we need to find autocorrelation function for phi u delta of tau. And now it becomes interesting, but we don't need to do anything else. Actually, the hint to find autocorrelation function of function in delay domain is the following. You simply substitute indices by distance between delta pulses, and you substitute these pulses is amplitude by delta pulses with magnitude. Is the same, with magnitude equals to amplitude of previous pulse. I just copy the same plot. I call it as, or I name as phi u delta of tau. Now you see that we working in time domain, in delay domain, sorry. Place all these all these pulses by delta pulses. And instead of difference in indices, I specify, I write a spacing between delta pulses. And if we look to our original problem, we see that the spacing between delta pulses goes to t. Instead of this integer quantity, we place t, 2t, 3t, and so on and so forth. T, five t. Also we have minus t, minus 2t, 3t. Yes. Yeah, sure. Why should we get negative values? I mean, in general, it's possible, but not for this example. But I mean, we don't have, for this specific example, all values positive. But you can check it. You can, it's easy. It's very easy to check. You just say, okay, let's continue and write for -1. Yeah. What you do for -1? You just shift to another direction. You just put 0, 2, 2, -2, and 2, 2, and then 2 and -2. Okay, what will be the result? 2 times 2, 4. 2 times 2, 4. -2 times 2, be -4. And the last product also -4. The result will be equal to 0. And if you just continue for -2, it will be 0, 0, 2, 2. And then what will be the element-wise product gives you 4, -4, 4. Result will be equals to 4. And you get actually exactly the same values. I mean, it will be symmetric. For this reason, I just made it for 1/2, but of course, you can choose which half, in which direction you would like to investigate this. Because we don't have imaginary part. Because we have pure real signal. And for this reason, correlation will be even function. Yeah, you can say this. Had some questions. We are taking part as well. Yeah, because I mean, you can just choose. There is no limit. Of course, you can say that our signal delayed comparing to first one, or we can say that first signal delayed compared to second one. And then you have this negative delay. It's absolutely fine. Because it just specifies a relation between two signals. PCF is a function, so we get symmetry around y-axis. Yeah, absolutely right. Absolutely right. And I mean, negative delay is not problem. It just says that second signal behind first one. No, other way around. It's just say that first signal behind second signal, and absolutely fine. Okay, let's go back to our problem. But it's good that you think about these questions and you ask them. That you think about these asked questions. So, yet instead of, as I said, instead of sample pulses, we put delta pulses. Each delta pulse has infinite amplitude. But magnitude of each delta pulse will be the same as for sample pulse. Right, like this. 20. Okay, and now this is delay, and as written above, this is function phi u delta of tau. Instead of indices, we have delay. Okay, fine. Was part C. Now we need to determine autocorrelation function of pulse shape. But there is nothing to do. I mean, it's just the rectangular pulse, and you already know how it looks like. Part C. Phi g of tau, function of delay. Let's show is just rectangular, triangular pulse. Goes from -t/2 and for amplitude of this autocorrelation function, we need to be careful because original amplitude was 1/2. We have to calculate square of it, and we also have to multiply by duration of our pulse. Result, we get that maximum value of autocorrelation equals to t/8. I mean, whatever it is, but you just need to be careful about it. Okay, fine. And that's it. I forget to subscript E. I think, yeah. Oh, duration of rectangular pulse t/2. No, it's spacing between delta pulses, t. But for rectangular pulse, it's smaller. It's t/2. But then triangle goes from -t/2 to t/2. So, and else. I see that if I write superscript autocorrelation of pulses. And now we go to question E. So determine autocorrelation of our original signal. Now we need to find autocorrelation of our original signal that I want to remind you as 0 times summation 4 times an times delta pulse t minus n delta pulses, and then it's convolved with our pulse shape. And you remember that if you have for your original signal 2 parts, or if you can represent your original signal as convolution between 2 parts, autocorrelation you can represent as convolution of corresponding autocorrelations for each part, autocorrelation functions for each part. Phi u of tau and write as times autocorrelation for u delta tau convolution with u of tau. And we have actually everything. You know what's the autocorrelation for part u delta, and we know what's the autocorrelation for pulse shape. And again, when you when you calculate convolution with delta pulse, you just replace delta pulse by second part of your convolution. Now we can plot how the resulting autocorrelation function will look. Determine scaling. Minus t. Okay, fine. Or we can also show that outside this range, okay, at 0, let's see what we have at 0. We have to multiply triangular with amplitude t over 8, is delta pulse with magnitude 20, and additional term, u0 squared actually, u0 squared. At 0, we have times 20. Write it as times t times 5. It's our phi u tau. And instead of delta pulse, we have triangle that goes from minus t over 2 to t over 2. Triangle. Our triangular. Then at t, what we have at t? At t we have 0, then we have nothing. And at 2t we have triangular times t times times t over 2. It's our triangular at 2t. At 3t we have 0. And at 4t again we have other triangle. Goes from minus t over 2. Its width equals to say that it's n so that's it. We have our autocorrelation function identical to what we had similar or similar. Now, so that's all. We have found our autocorrelation and we have specified all the parameters. Okay, any questions? Was fine, not so difficult. And we go to next task. Next task will be task number 3.6. And for this task, we need to determine autocorrelation and corresponding power spectral density of the following signal. And here we get interesting, or we come to the point that we start to working with periodic sequence. Now we have this infinite periodic sequence of delta pulses. Starts from nowhere and goes to also nowhere. No start, no end. And let's try to analyze, try to find what's the autocorrelation function for such sequence. Have just of delta pulses. Period of this sequence, or spacing between delta pulses. It's very easy to show this function, but let's again try to analyze what we need to find. We need to determine autocorrelation function and power spectral density. And you see that here we start talking about power spectral density, because if you take this infinite sequence and if you try to calculate energy, I mean, it's infinite, because for one delta pulse energy will be 1. But then you have like infinitely many components and have no limit. But if you divide by period, then you find you have finite power, and you can just express all these parameters in terms of power. No problem. Okay, is there a major difference in the impulse moments or pulse weights of the Dirac delta pulse of the autocorrelation if you compare this autocorrelation pulse? Okay, and then we compare it to result from previous task for only one delta pulse. Okay, actually we're going to do exactly the same steps as we did for task number 3.3, very beginning, because what we took our pulse, calculated spectrum, then we took absolute value squared of this spectrum to find energy spectral density, but for us, we're going to find power spectral density, because we have periodic sequence. And then from power spectral density, calculating inverse Fourier transform, we find autocorrelation function. So we just follow all the same steps, and let's see what we get. And let's see if we get actually different result. So first, we're going to plot our sequence, delta pulses. Pulses, and magnitude equals to delta pulse not duration, so spacing E small t subscript p. What else? We also say that it's our signal subscript p time domain. Now we calculate transform to find spectrum. So we calculate Fourier transform. We're going to from time domain to domain. And again, we plot. And before we plot, just look to our table of basic transforms, and we see that if you have infinite sequence of delta pulses, after Fourier transform, you get another sequence of delta pulses with different spacing and different magnitude. But you can find, because spacing will be inverse of period and time domain, and magnitude will be normalized by spacing original magnitude divided by spacing between delta pulses in time domain. You can determine this sequence in frequency domain. Specify. I show that we get sequence spacing will be spacing between delta pulses will be 1 over E subscript P. One over T. And what will be the magnitude? Oh, not TP. That's very close. This is in time domain. It's in frequency domain. And what will be the one over TP? Exactly. How you get it? You just divide both parts by, in this case, UBT0. You just get one here, and on the right side, you get 1 over, in our case, it will be 1 over T subscript P. And you can do whatever you like if you apply this to both parts at the same time. You can multiply both parts by something, divide them by some scalar, and not a problem. You just divide both parts by subscript P, then you just can use this expression to find what will be the magnitude. Is 1 over our magnitude. And next step, calculate power spectral density. And to calculate power spectral density, we calculate square absolute value squared of each discrete component in our calculate absolute value squared of each discrete component in our spectrum. Then what we get? We just square magnitude of each delta pulse. For spectrum, now we come to power spectral density. Yes? What? How? Do you want to approximate by rectangular pulses? The problem is that the problem is that you have infinite sequence. For previous task, we had 5 delta pulses, but here you have infinite. And the question, what you do, how you, I think it's probably possible if you just sit and think carefully. I think you can also do it. But like if you just right now just thinking about the moment may not be so. But maybe not. Maybe it's easy if you know some hints. Maybe, but because now I see that actually it will be the easiest if you just go to the first task that we considered today and just apply the same. Because I mean, then it will be just very simple. Go to spectrum, to power spectral density, and you already find out the correlation. You don't need to try to figure out what you do with the sum of infinite components. But in the end, yeah, you mean then later on we just based on these results, I think we will start. Let's see, maybe we start using slightly different ways how to get this result. But of course, sometimes it takes more time. Take you more time to write all this. I mean, now here what we calculate this pi u. This is without superscript e. This is power spectral density. And for power spectral density, you calculate square of each delta pulse, square of magnitude for each delta pulse, and absolute value of square. Yet that we have this. Another set of delta pulses is the same spacing, but different magnitudes. In this case, magnitude will be 1 over e subscript t squared. This is just calculate square value of each. Okay. And finally, in order to find autocorrelation, we perform inverse Fourier transform. We go from frequency domain to delay domain. And my question will be, what the resulting magnitude will be after back transformation, after this. What happens with magnitude? You can just use basic Fourier transform that we have and try to answer this question. This is now phi u of tau. Okay, and magnitude for power spectral density was 1 over Tp squared. And then we go back to the domain. Then question, what will happen then, this magnitude? Louder. Yeah, but what happens, we just take our magnitude and multiply by spacing between delta pulses. 1 over Tp squared times T subscript P. And then it will be 1 over subscript P. This is the result that we get. Delta pulses. And what do we see? Maybe just to analyze results, I will repeat the result for one delta pulse. If you have one delta pulse, magnitude 1, after transformation, after calculating autocorrelation function, is that I delta delta of tau. Actually, autocorrelation function has magnitude, in this case, the same as for original delta pulse, 1. But what happens with our sequence of delta pulses? It has magnitude Tp times smaller. That original sequence, each delta pulse had magnitude 1, but after you calculate autocorrelation, magnitude for the sequence will be 1 over T. So you just normalize by spacing between delta pulses. And this is a conceptual difference between autocorrelation for periodic sequence or energy signal. Because again, what we say that if you take a periodic signal or random signal, general energy will be infinite. And as a result, autocorrelation also will be infinite. And in order to avoid it, we just start operating with power. Here we normalize period or spacing between delta pulses. Okay, any questions? And now it was all for task number 3.6. Now we go to task 3.7. Yeah, and now, starting from now, you know what to do for periodic signals. Now we go to task number. Consider the following periodic time sequence, and the main world is periodic. Now we consider periodic sequence, and it's given by the following period denoted by n equals to. Say that equals to a plus k capital N. So every capital N symbols, we get the same symbols. Sequence or one period given set of numbers. Minus plus 1, 1, minus 1, plus 1, plus 1, minus 1, minus 1. Total, we have 7 elements. So, and we start all the same, but for periodic signals. First question, we need to determine discrete time autocorrelation function of the periodic sequence AN. It is defined as discrete time normalized by spacing or period of our signal, not 4 but 7, plus m. Okay, great. And just do the same table as we did before. But in this it lines. What? It's m. Minus 1. There we calculate A. Calculated. Seven. Okay. So let's do shift by 0 in the same sequence. 1 minus 1, 1, 1, minus 1, minus 1. Okay, what will be the result of this element-wise product and summation? 7. No, not 7. Because, yeah, I mean, summation will be 7, but then we have to also normalize by number of elements. So it will be 1. 7 divided by 7, it will be 1. Okay, let's go further. We shift by 1. We shifted, but we just can check off to the left side. Yeah, have minus 1, 1, 1, 1, minus 1, minus 1. And what should I place to the last position? 1, because this is periodic signal. And if we just move by 1, on the right side, we get beginning of another period. And for this reason, we write from another period, it comes 1. But for energy signal, we have nothing, and we would place 0 for energy signal. But for periodic, we just write beginning of next period. Okay, let's try to calculate element-wise product. Minus 2. I get minus 1 divided by 7. Do you have the same result? Okay, yeah. Cut. Okay, great. Now let's go further. We shift by another. And we write, we get 1, 1. 1. This is period ends. Then we write first two elements from the beginning next period. First element will be 1, minus 1. Again, we calculate element-wise product. And I actually can, you can check it by yourself, but I do the following. That every point, for every point from, starting from shift 1 up to shift 6, we always get the same result. I would recommend check it at home. Always will be equal to minus 1 over 7. You can check it, and if I'm wrong, just let me know next time. And when it will be shift equals to 7, and we get again result equals to 1. Shift by 7 elements corresponds to exactly the same sequence. So we have top 1, 1, minus 1. Okay, and we get this interesting autocorrelation function. Now, let's see. And first of all, you already see the difference because for energy signal, autocorrelation had maximum value and then it went to 0. You can say that if you take in difference between indices big enough, resulting correlation will be equal to 0. But for periodic signal, autocorrelation function will be periodic. See that for difference between delays between indices equals to 0, have result equals to 1. And then when difference between indices equals to 7 equals to 1 period, autocorrelation again has maximum value. It's again 1. And then we actually get that this autocorrelation is periodic. On every period, every delay that equal to period, you will get maximum autocorrelation. Okay, let's see what we need to actually find. Determines the discrete time autocorrelation function of the period sequence. Okay, we already have it. And plot it, or we can just go directly to. Okay, let's plot it because. Maximum or our pulse amplitude 1. Then for difference 1, 5, 6. For all of them, we have amplitude minus 1 over 7. And for 7, again, we have value equals 1. Negative range. Seven we have 1 minus 1 over 7 all others. Okay, this is our discrete time correlation function. M, function of index. Okay, now for part B, we need to find autocorrelation function of the sampled signal. Sampled signal, time domain. F equals to And in order to get this autocorrelation function, we just use discrete time autocorrelation function, and we normalize by spacing between delta pulses. So we just keep the same shape of our autocorrelation function. We replace each pulse by delta pulse and normalize by spacing between delta pulses. And then when we plot it, I mean, I just repeat this plot. But instead of each discrete pulse, I put delta pulse. And original amplitude was 1, but for this resulting autocorrelation function, I put 1 over capital T. I also normalize. I normalize by spacing between delta pulses. Seven times 1/t. And instead of discrete pulses, we place delta pulses. 5, 6. 5, 1. Everywhere we place pulses. Going to plus infinity. And spacing, above we have spacing in terms of indices, 1, 2, 3, 5, 6, so on and so forth. But now we have the spacing in terms of delay that equals to capital T. Now we have X. This is our autocorrelation function of tau. Okay, great. And most important, find discrete time autocorrelation function. And then after you normalize amplitudes by spacing between delta pulses and replacing indices by spacing between delta pulses, you get autocorrelation function of this sampled, how was it called? Sampled signal. Okay, and finally we come to part C. I think we have 10 minutes to come. Part C. We need to find autocorrelation function of the whole periodic signal if we assume that we also, for this sequence of periodic symbols, we apply or we use specific pulse shape function. That has some times G minus N as UG times rectangular shape function divided by capital T. So what do we need to find this autocorrelation function? What's the steps make this last result? Our goal is to find autocorrelation function U of tau. I know that you know it. But why? I mean, could you explain why we can just? No, you said that we can replace each delta pulse by rectangular, but it's not true. For autocorrelation function. Okay, for U of t, but what it means? That what do you mean by saying this? Not multiplying, because it's already. I mean, if you say about multiplication, then you just look to original expression because it's already g of t already there. You don't need to multiply anything because it's already there. But what need to somehow convert this representation slightly different form, and then we already it's just very easy to get there is the final result. Any ideas? What should do? Directly for this expression. Wait a second. This is how you do Fourier transform if you have just unfinite sequence of rectangular pulses. What will be the Fourier transform of it? Because I don't know what is the Fourier transform. Maybe is I'm asking to. This is exactly what I'm asking. Like, what will be your steps to find this autocorrelation? And a small hint: you don't need to go to frequency. Already, you have everything without Fourier transform. No, very simple question. It's not difficult. Just I try to understand. Okay, you see this question at exam, and then like, what's your steps? Hope you don't go to next task. Just after seeing this question. Where should we replace rectangles? But for part B, this is autocorrelation function. Autocorrelation function. No, it's not difficult. Why it's so? Why I didn't get answer yet? In the question is very simple, and we used this hint like for last 3 tutorials. I think we used this hint every time. Come on. I mean, is it so simple so you don't want to answer, or is it so difficult so you don't know what to say? Or maybe someone in the chat maybe have answer. Participants discuss online. Oh, well, hi. Have idea what we should do? Because we have problem. Sorry? No, you don't need to get power spectrum. You just you need to somehow modify this form. Then everything becomes super easy. It's not difficult. Someone open microphone. Yes. Do we have answer?
Sir, I'm not sure, but I'm trying it. Since this is going to be a rectangular pulses, series of rectangular pulses. Sir, is my voice audible?
But it's difficult.
Since this is going to be a series of several rectangular pulses. So I think it will be uh, autocorrelation of those successive rectangular pulses resulting in triangular pulses.
You are at the right way. You on the right
E-
path.
Actually,
Uh,
for two rectangular pulses of same duration, we will be getting a triangular pulse. So several successive triangular pulses. Uh, I'm just trying it. Not sure.
okay, but thank you for this try. Yeah, thank you.
Hello? Hello? Can you hear me?
We get the answer that if we look to this original expression, we actually can represent it as convolution between rectangular pulse and sequence of delta pulses. And we did it for many times before. And also we do it for next tutorials, we probably do it every time. Yes, this is exactly what supposed to do here. We can just rewrite that. Okay, yeah, thank you. We can just write this u of t as summation goes from minus times delta pulse t, put big parenthesis, convolution with, that's it. I mean, you know what the, no, I mean, and then we say that the autocorrelation for u of t is convolution of two autocorrelation functions. We already know what the correlation function for this part called as u delta of t. And it's very easy to calculate autocorrelation for rectangular pulse. It's just triangular shape function. And that's it. Actually, what we need, we just need to write what is the rectangular part, rectangular shape. Pulse shape function, g phi g tau. And we have for rectangular pulse that goes from minus t to, no, it goes from minus t over 2 to t over 2. Fine. So it goes from 0 to capital T. Thank you. And oh no, sorry, it is for rectangular pulse, but for correlation, of course, it will be from minus t to capital T, u0 squared times capital T. Fine. And what we do, have this expression for autocorrelation function, or we have this plot for autocorrelation function phi u delta of tau. Then we just, each delta pulse we replace by this triangular and multiply by corresponding magnitude. Let's finalize, let's make this plot and our tutorial. Okay, and triangular function. Of another of each delta pulse replace function. They're actually overlapping. Overlapping. 1, 2, 6. So what we see is that they overlapping, and as a result, I draw them overlapping functions, but then we have to reconstruct envelope of the resulting function. This is how it looks like. Now let's try to understand. And as far as you're working with linear functions, it's very easy to reconstruct this envelope. Just take point, have 0 from other component. Part itself by itself, because it's just at this point we have no other components. They're all equal to 0. Connect the points, all other points. Function will look like autocorrelation such periodic sequence, like it's red, has maximum at points closer to period. All other points it will be equal to minus 1 over. See what actually calculate what. How it looks like. Okay, now this is autocorrelation phi u tau. Okay, and now we need to calculate all what's the of rectangular of the autocorrelation function for rectangular pulse times maximum for autocorrelation sequence. It was 1 over t. 1 over t. As a result, maximum will be to u. And let's do similar calculations for the lower and minus 1 over 7 1 over t times u0 times t. Get that itself will be minus u divided by 7. So that's it, and get everything what we need to find. Times u0. How resulting autocorrelation function will look like, or periodic sequence of these symbols. Yeah. And what else we can say? We can also specify and this effect very often for synchronization, because if you have a sequence with very good autocorrelation properties, then you can easily detect moments where you receive your signal, because in comparison, because noise usually won't correlate so much with this sequence, and this sequence correlate with itself very good. And then you can just putting threshold, you can try to find this start of your signal. Okay, that's all for today. Thank you for your attention. Are there any questions?
Damir?
Yeah, Bilal, I saw
Sorry.
your question.
Yeah.
I just let.
at
Or
the
do we
end.
need students to discuss?
Yes, yeah, because I wanted to share this with the students. Unless somebody has any question about this, what you have now, I would like 1 minute of their time.
Okay, yes, there's now we're doing survey on for videos program for online participants, and Bilal going to give you more details. Yeah, Bilal, please. Floor
Thank
is
you.
yours.
Is this slide visible to the students who are present in the lecture hall? Damir?
I try to understand. Yes, sure. We can make it visible. Yeah, Bilal.
Yeah,
Go ahead, please.
please. I have also sent an email, but not everybody is copied in that email because I don't have the email address of all the students who are taking the classes on site. So we are conducting a survey to help us improve the study program. It's open until this Sunday, so it would be great if all of you could take part, the online and on-site students, so that we can also compare and contrast your experiences. So Damir can share this in the Moodle for the course as well, this slide, if you're not able to scan the QR code probably like this. So that was it. Just a short reminder that please, it would be great if you guys can.
Yes, sure, Bilal. I also upload it to Moodle.
Thank you.
Okay, Bilal, do you have anything else or?
No, thank you.
Okay. Okay, so yes, I also upload this slide and it will be available. And please participate in our survey because it's very important for us to get feedback from you. Okay, are there any